Okay, so today uh, we are going to do a lesson on efficiency. All right. By the way, I got my little video running here of me. This is my basement. By the way, it's the only place that's pseudo quiet, but I apologize if there's creaky steps and babies crying and stuff. Doing my best here to try and record these videos. At any rate, so the efficiency, right? So there's three different algorithms on the AP test: selection sort, insertion sort, merge sort. So far, we've just talked about selection sort. You can see a review of it, right? It selects the minimum one at a time and puts it in place, then finds the min of the remaining numbers, right? Because there's multiple ways to sort numbers, it makes sense to think about which one's the best or most efficient. And there's really be two ways to do it. One, you could think about how much memory it's taken up, like how much space memory is used in the computer. And then also you can think about like how fast it is. All right. And so we're going to more talk about the second type, like how fast it is. And we're going to like roughly gauge that by how many times it has to compare numbers, right? How many sort of operations the computer has to run in order to sort them. All right. So in class today, we are going to do two different things. One is we are going to just literally time it, right? We're going to use the stopwatch class to time how long it takes selection sort to do a different number of values, like sort 10,000 to 20,000 values, right? This might be really fun. If you've written your own selection sort, you would have to alter some of the starter code today, but you could try and time your own selection sort if you've written one. Okay, and then the other part of this, sorry this didn't fit all on here, but there's something called big O notation that I remember doing this a bunch in college, which is just to like try and weed through the code and say like if there's n numbers, how many comparisons will it take? How many computations will it take to sort them? And so like if there's n numbers, right, a really good algorithm would only take maybe like 4 times n comparisons or computations. And then a little bit worse one would be if you were squaring n, and then it slowly gets worse from there, like if you're cubing it, right? And then the really bad one would be if it was something like 2 to the n. So every time n increases by 1, you multiply by 2 more comparisons. That'd be really bad. Or something like factorial is actually really bad too. Um, but yeah, we're going to do a little bit of math and try and figure out like what is the big O notation for n numbers? How many comparisons is it for selection sort? Okay, so why this matters, right? So I think I talked about this briefly before, but basically your cell phone, if you clicked on an app and it took even a couple seconds to load it, or your game ran slow, it's just not going to work. So you want to write stuff that's efficient, that runs quickly, so it gives the user like a good smooth experience, right? In the world of cell phones, this matters a ton. For a while, computers are getting so fast it didn't efficiency hardly seemed to matter. But now that cell phones aren't quite as powerful as a desktop computer, some of them practically are, but um, because you have limited memory, you have limited computing power on a cell phone, you want to make stuff efficient. Okay, so here's the activity part. Hopefully this all makes sense. What you're going to need to do is go into Eclipse, make a new package called timing, and then you go out to the starter code, and this should be in chapter 14. You'll have to find it. I'll put a link probably right in the folder for today. I can put that link right in there, and you could go there and find it. But um, there'll be more than these files there. There'll be a bunch of them. There's one for insertion sort and one for merge sort, I think. If you want to get them all right away, you can. I think to be files total. For today, we just need something that'll make arrays for us. That's called array util. The thing that this is the one you'll actually have to modify. Not really modify much, just change a number in it, and then a stopwatch which will time how long it runs. So kind of the idea is you're going to go into selection sort timing, and you're going to set the number of items to 10,000 and run and see how long it takes. And it won't take very long, right? It'll take, just fractions of a second or something like that. You might want to do a couple runs and just sort of average them, right? Keep it at 10,000, run it, say, 3 or 4 times and get a rough sense of what the average is. And then change the number of items to 20,000 and do the same thing. And then we're going to go 30,000, 40,000, 50,000 from there. Okay, so what you're really going to need on your piece of paper here is to do a table, right, of n this is how many items we're going to be sorting. Computers are really fast, so we're going to sort 10,000, 20,000, 30,000, 40, 50, 60, and then you need to record how long it takes. Okay, so you're just going to run it and then record your time in this table, right? And long term, we're going to make a graph and we're going to see what it looks like, right? If it was like n elements and say that it only took 4 n comparisons, then we would get a linear graph, right? Which for all you math folks, that would be something like that, right? And if it's an n squared, we might get a more quadratic looking graph, something more like that, right? If it was something like, say, 2 to the n, an exponential, then it would just be skyrocketing like that. So we kind of want to just make some sense of what's happening here by recording how many seconds it takes, right? So do that first, and then we'll talk about how to make the graph. Okay, so just to show you what it looks like in Eclipse, here's my little package. And again, I've loaded insertion and merge, which we're going to do later. If you want to do that today, you can. If not, you can do them when we do them in the later lessons. So at any rate, this is the only thing you ever need to edit, actually, is just num items. So you can just run it. You can see my computer, how long it takes here. So you can run it a few different times, try to get a sense of it. So I ran it a few times. I'm going to call it about, I don't know, 1300ths of a second. So that's what I would need to record on my little sheet here. So let's see if I can erase all this mumbo jumbo. But all I'm really doing right now is recording roughly how many seconds. And this doesn't have to be exact, right? And then go back in here and try this out. And your computer might be faster than mine, might be slower than mine. Some of this will depend on the computer, but hopefully we'll get a consistent pattern here. That's actually taking me quite a bit of time. Not very consistent. Wow, not consistent at all. I think it's maybe because I got this recording thing running right now too, which is also eating up computer space. So I don't know. That could be a problem for me here, but I'll call that about, I don't know, 0.3 of a second. All right, so I'm going to go back, record it. Okay, and so your job is just to do that on your own. All right, pause the video, and then once you got that, you can resume. All right, so what I want to show you now is make a graph. So you could draw it by hand, but you'd have to draw it super accurately, right? So I actually filled in some numbers from last year since my computer's on the fritz now. They just can't handle running all these things at once. But anyways, we're going to graph them using, I think Desmos will work pretty well if you don't want to do them by hand, right? So I'm just going to demo how to do that. So use your numbers, not mine. But basically go to that Desmos calculator. Oops. Okay, so go to Desmos, right? It's just desmos.com/calculator. Hopefully you can see the address there. And then what we want to do is we want to do a table. So to do that, I'm going to do this little plus and do a table. And then I'm just going to start typing in my numbers here. So I had 10,000 items, and I think that took like about 6/10 of a second, sorry, for my computer. And then type in 20,000. And I think, what was that? I forget. Let's go back. 2/10 of a second. All right, and then next one, 30,000. Blah 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 blah. Maybe I'll just pause the video and fill them in here quick. But you just do the same for your numbers. Okay, so you hopefully got them all filled in. Again, I did that by getting here and adding a table and enter them in. All right, so you can see, hey, West Patel, I don't see anything. Okay, so the reason for that is the scale. All right, so the trick is, our X numbers are going from 10,000 to 60,000, and our Y are going from 0 to, just a little bit more than 1. All right, so didn't quite show up here, but way on the right, you have a graph settings here, the little wrench thing. So if you click on that, and then you can change the x-axis and the y-axis right here and here. So sorry if this is hard to see, but I'm gonna have my x go from 0 to so like I'm gonna do like 70,000 maybe. Make it go up. Now you can see my points starting to show up. And y, I'm gonna have that start at 0 and go to about 2, right? And so then you can get a little bit better picture. So I can scroll it now. Hopefully you can kind of see, all right, what it looks like. All right, and you can try and guess, right? What do you think this is? Does it look linear? Does it look n squared, n cubed? Right? Take your best guess, right? Hopefully you have something that looks similar to this. All right, so hopefully you had a chance to think about it. And what happens is this is actually n squared, right? So the like the big summary of today's selection sort is actually an n squared algorithm. All right, and we'll talk about why that is in a second. The official formula is looks like this. So if there's n items, this is how many computations it'll take for selection sort. But all that really matters is the n squared part. And the reason for that is as n gets big, all of this stuff won't make any difference. So if we just took even our smallest one, which was 10,000, right? And if we plug 10,000 into this formula, we'll have 1/2 times 10,000 squared, which would be a 1 with 8 zeros, I think. Call somebody smart if you think that's wrong, but that's right. So that's a monster number, and then obviously we're going to take half of that, right? But we're going to take half of that, and so the rest of this does not even matter, right? 5/2 times 10,000 is going to pale in comparison to that first number, right? The n squared part is huge, and obviously the -3 is tiny. Okay, so as n gets really big, what happens is these parts are not even significant, so we don't even really consider them, and even the 1/2 doesn't matter all that much. What really matters is the fact that it has an n squared in it. Okay, so when they talk about the efficiency of an algorithm, they only really look at sort of like the highest exponent or the highest contributing factor, right? If this formula had like a 3 to the n in it, then all of the rest of it wouldn't matter because this would get so big really, really fast. And so all what would matter is that this would be an exponential. Okay, and so another way to kind of look at this, there's our graph, is I thought this was pretty cool. I saw this on the internet where here's the different what things that could happen. The best would be like a log one, where you take log of n, as n get big, the log would make it really small. This would be like a linear one, and then n times log n is here, right? And then you can see n squared. So you can see that, you know, as the number of elements gets bigger along the bottom here, sorry that didn't quite show up, but maybe I can move this up. I'm not an idiot. Okay, so this out of the way. So you can see that as n gets bigger, n squared is going to be much, much worse than a linear one, right? And 2 to the n is far worse, and n factorial is actually the worst of all of them, right? So the point is, as n gets big, it makes a huge difference, right? So Google's algorithms are down here running really fast, right? Algorithms Mr. Westphal would write would be a lot slower, and then something that say like Mitchell would write would probably be like up here. But at any rate, you want to write an efficient algorithm, and there's actually ones much, much more efficient than selection sort, right? For us today, this is what selection sort fell into. Okay, so from today, I hope you were able to do the analysis, make your own graph in Desmos, and it's kind of fun. See how your computer compares to mine, see if you got faster or slower times. But that's pretty much it. All right, and I'm going to do one more video, and that I'm going to do kind of like a dive into why this is n squared to like actually look at the code, right? So I'll do one more short video about that, and that'll be the final part for today.